So as Andrew said, we have some big goals in this. The overarching goal and maybe the context that I want to kind of view this work through is that one wants to classify all, and I'm going to write PTC for pre-Tanakian categories. Right, and I would say maybe this is something that a lot of other people have sort of touched on, and I think a lot of this work that's been happening in the moderate growth setting, understanding incompressible categories, can also be, viewed as part of this. Right, this is maybe a goal for the room, not a goal for this talk. I'm not gonna do this in this class, but I think of this as a sort of guiding problem in our field. We want to classify and understand pre-Tanakian categories beyond the Tanakian case, beyond representations of groups. And I think maybe the more modest goal for this talk is that I want to convince you that oligomorphic groups have to be a part of the answer. Whatever classification of pre-Tanakian categories might be, it's going to involve some oligomorphic group data, and this construction that Andrew just went through is not some, the oligomorphic groups are not some artifact of our approach, but really like a fundamental aspect of this theory. And so that's maybe, hopefully, the takeaway of this whole story I'm going to tell you. All right, so in order to do that, though, I'm gonna go away from the world of pre-Tanakian categories for maybe the first half of this talk, and instead I want to talk about something sort of much simpler. But let me maybe motivate it by giving some explanation. So if we're interested in representations of groups, and I hope we all are, right? One sort of, you look at representations of a group and you say, okay, that's a nice category. It has extra structures on it. And then when you sort of axiomatize what those structures are and the properties they satisfy, this sort of gets you to the definition of a Tanakian category. And then, of course, if we kind of relax, this requirement of having a fiber functor to vector spaces, so if we require our category to be sort of realizable as a collection of vector spaces with linear maps between them, then we get representations of groups on the nose, or finite dimensional representations of groups on the nose. But if we relax this realizability condition, we see there's more stuff, the kind of pre-Tanakian categories. But OK, so this is the sort of linear story that I think most people in this room are familiar with. But I want to kind of I want to go even easier. So if I look at G sets, so now I'm thinking of G as being either finite or profinite. I can look at the category of G sets, and I can do the same thing. I can try to sort of axiomatize what sort of categories arise as categories of G sets. Okay, and this leads one to the notion of a Galois category. Okay, so I'm going to start, I want to leave the world of anything linear, anything tensor category. I want to go to this sort of discrete world where I'm trying to understand sort of categories of G sets, but from a categorical perspective. I want to figure out which categories are categories of G sets. And I'm not going to assume most of you know this story, because it's maybe less standard for this crowd. So I want to go through what this is before sort of generalizing it to what we call pre-Galois categories, which are going to be the analogs of pre-Tanakian categories, but in this kind of discrete version instead of linear version. But OK, so what kind of properties of the categories of G sets? So again, we're thinking of G being like a finite group, maybe profinite. What are properties of this category that we can say? So a big thing is, so I'm going to start kind of listing some off, and then that we're eventually just going to take this collection to be a definition. So for one thing, we have a coproduct. Right, so if X and Y are G sets, we also act on their disjoint union. Right, nice, well-behaved. All right, and then another important thing about G sets is that, so maybe when I say G set, this is a lowercase s. I'm really thinking about sort of finite sets being acted on by a finite group. And that means that you have finitely many orbits, right? So every G set is isomorphic to, I'm going to write it as x1 disjoint union x2 disjoint union xn. So it breaks up as a finite union of orbits where each xi is transitive, which I'm just going to mean can't be broken up further. So right, so I think we call, when we sort of are trying to get away from the language of G sets, we call these atoms, just in the category of G sets. But so we're really thinking of them as sort of, the basic building blocks of any finite G set is the transitive ones. What else do we have? So we have.
Do you want these decompositions to be unique? Essentially unique?
Yeah, essentially unique. I'm sure. Some of these things will follow from other things, but I'm gonna take the stance that it's okay to add extra axioms. We're not looking for a sort of minimal description. But OK, so we have finite coproducts. We can also take products. So I have fibered products, like, so if I have X going to Z and Y going to Z, then X times Y fibered over Z exists. So I have fiber products satisfying the right universal property, and then, but in particular, I want to say one special thing about groups sets of G sets is that this fiber product is non-empty if x, y, and z are all transitive. So if they're all transitive, then sort of everything, there has to be stuff in x and y that goes to the same thing in z. So and is non-empty if x, y, z are transitive. All right, so that's a nice property. I guess I should also say there are a couple distinguished G sets in the category of finite G sets. So there's we're going to count the empty set as a G set, and also we have what I'll just denote by a point is also a G set, and the point is going to be terminal, right? So this is just a point where G does nothing. All right. I wrote a list because there's a bunch of these. I can't remember. I should make sure I have them all.
And the empty set is initial.
Yeah, the empty set is initial. Right. Another. Also, actually, a big one about these transitive sets that I can't believe I skipped is that if you have two transitive G sets, and I have a map x to y, this is a monomorphism of transitive G sets is an isomorphism. Right? You can't include one transitive set in another transitive set, but you can project a transitive G set onto another one.
But we don't have a G, right?
Well, right now I'm just listing properties of the category of G sets. You're right. I'm going to take this to be a definition in a second, but all these properties that I'm listing are should be kind of familiar, nice things that we recognize. Yes, finite G sets should definitely satisfy these properties. In the same way that when you read the definition of a Tannakian category, sort of assuming you're sort of comfortable with the language of tensor categories, it's very obvious that finite dimensional representations of a group are a Tannakian category. That's you're oh, of course. Pre-Tannakian or, well, I would say finite dimensional representations of a group are Tannakian.
By definition.
Yes. This is because you carefully chose your definition.
So you didn't discuss the tensor product yet?
Yeah, I'm not there yet. I got a couple more.
Oh,
Yeah, so we also, in addition to having the co-product, we also have product. Oh, I did discuss it.
Yeah. When Z is the point.
When Z is a point, you have x times y. So this is, we have finite products. This is going to be the sort of analog of the tensor product. Right, so we're okay.
Wait, but this is final product?
No, with the empty set, not the point.
Oh, with the empty set.
Which doesn't exist. With the terminal.
No, with the point.
No, the point. Because the point
No,
is
the
never
point.
the empty set.
Yeah, the point is,
Yeah.
take fiber product over the point. That's the ordinary product.
Yeah, that's right.
Okay. All right, and then I have one more kind of funny thing that we're going to need that I don't want to say too much about it. But this last one is that equivalence relations are effective Okay, this is maybe the hardest one to motivate. But what you can imagine is if you have a subset of x times x, and it's an equivalence relation, satisfies the usual transitivity, reflexivity, things, then you can form the quotient, right? So then so equivalence relation.
G equivalent. Yes?
G equivariant, yeah. So an equivalence relation in our category of G sets. Equivalence relation. Then we can form, X mod R, and it has to satisfy the right kind of universal properties. So this is sort of obvious for G sets. You just take the quotient as a set. But if we don't have access to sets, if we sort of forget about the fact that we have a functor to sets, it turns out we need to impose something like this. All right, and then the last property of the category of G sets that I want to highlight, assuming I didn't miss anything when I was writing my notes, is that we have a functor. So there exists a functor omega from G set, from G sets to sets. This is just the forgetful functor, and it needs to be, the properties we want are exact and conservative. And let me just say, so exact means it's going to commute with finite products and coproducts. And then conservative basically says that, well, if the image of some map is an isomorphism, it had to be an isomorphism originally. This just means if you have a map between G sets, and that map is a bijection, then the inverse map is also G equivariant. Right? So this is maybe a nice exercise for an algebra class where you're learning about group actions. But that
exact, does it have to commute with this quotient construction also?
Yeah, so it really should commute with all finite limits and colimits. So, but you can test it on a smaller. But yeah, so these, hopefully none of these should seem that weird to you as like, these are properties that the category of finite G sets for a group G has. But now I'm going to just sort of take this as a definition for something. Did I miss one, Andrew? Which one?
Did you have a map from a transitive G set into a disjoint union?
Yes, very important. Yes. So I have a map from X to a disjoint union of Y and Z, and X is transitive. Then it factors through one of them. Kind of, and it's or like really exclusive or one or the other in a unique way. And this is sort of getting at when you asked, is this decomposition unique? That's really sort of encoded in this axiom, but. Yes.
So is this mapped to finite sets or just to sets?
Finite sets for this case.
Because we have the rigidity in that world, linear world. Rigidity means that we have finite dimension vector space.
That's right.
So here you should be finite sets. Yeah?
That's right. Yeah. So if it were capital S, it would be all sets. I'm following that convention, the capitalization one. Yeah. So this. If I just take a category that has all of these structures, this is what we call a Galois category. So this is the definition of a Galois category. So I will say, so this notion of the Galois categories is due to Grothendieck. This is in SGA1. And it's not this, but it is equivalent. So again, I was sort of saying, for these types of things, I'm not so worried about trying to find a minimal axiomization, but anyone is kind of OK. And this is the one that we want, so that's the one that I'm going to tell you. And so these axioms give us a definition of a Galois category. And then the theorem is that if C is a Galois category, maybe I'll include the
point G set is like a terminal object. That's what you mean, like in the general case, when you don't see these as sets.
So this point is just a point with the trivial G action.
Yeah, but as a generalization, when you say, okay, I take these axioms.
You want existence of a terminal object?
Yeah, I want existence of a terminal object. Right, so I was sort of hiding it here. I have a terminal object. Okay. That's part, I'm listing it as properties of G sets, but secretly I'm thinking of them as axioms. But yes, you're right. So it could just be a formal symbol for a terminal object. But
it's gonna be sent to the 1 point set under this functor because it's a kind of a limit to it.
It'll have to, yeah. Great, okay.
So, more generally, being a Galois category is a property, there's no structure. It's a property of a category.
I guess you need, basically. You have the fiber functor.
Pre-Galois.
But is this fiber functor unique if it exists?
Well, yeah, let me.
So it is also.
Let him write down this theorem.
Yeah. So theorem is if I have a Galois category with a fiber functor, then, well, C is equivalent to a category of G sets where G is equal to the group of automorphisms of this fiber functor. So right, if you really love Tanakian formalism, this is exactly what you want it to be.
It's a profinite group, yes?
Yeah, that's exactly what I was going to say, is that this is a profinite. But if you assume some further finiteness properties, you can get it to be actually finite. But yeah, in general, it'll be profinite.
So is there some intrinsic characterization of the existence of the fiber functor?
I mean, so yeah.
So there will be you will introduce a notion of pre-Galois basically, yes?
Yeah. You want to give my talk? Right. So this is sort of classical. This is due to Grothendieck, and kind of the motivation for this is how they define the Étale fundamental group. So this is like, you know, this is the motivation on that side, is to define kind of what fundamental groups are in algebraic geometry when you don't have access to like a complex manifold, right? It's this whole formalism. Okay, so that is the background, where we're starting for this. So okay. So now we have Galois categories, and we know that they're secretly categories of G sets for some set. So if you like, pre-Tanakian categories, you then want to know, well, what's the analog? So definition: a pre-Tanakian category, a pre-Galois category, I should say, pre-Galois Galois category is all of these things, but not the last one necessarily. Satisfies everything but that pesky fiber functor axiom. Okay, so that's our definition of a pre-Galois category. I think it's pretty natural. So it's a category that really looks and smells like the category of finite G-sets for some group, but we don't have a way of sort of realizing it as a collection of finite sets with maps between them.
So this monomorphism of transfer sets being isomorphism, it's somehow saying that if you have like one decomposable state inside another, it's like that. That's not always true in some sense, right? Like why is that like?
If you have a transitive G set sitting inside another transitive G set.
I'm just saying, like in a pre-Galois category, why do you need to impose that condition?
I mean, we want it to be. That seems like a pretty important part of.
Okay.
I mean, you can drop any one of these, and we do kind of have various gradations of when we drop some of these. But I don't know. I think that's a pretty natural thing to want to keep about G sets. Great. Okay. So we can think. Okay. Well, what are some pre-Galois categories? Okay, an example. Well, any Galois category is automatically pre-Galois, so that's not interesting. But maybe based on the context of me giving this talk, you can guess that if I have, so I'm going to look at G set, and I'm going to look at the smooth ones, where for G oligomorphic, or maybe I should say admissible, O/oligomorphic. So it turns out, for a lot of the same reasons that it's true for finite groups acting on finite sets, these oligomorphic groups, they're categories of smooth G sets. So again, smooth ones are the ones where the stabilizers are open. We have this topology on our admissible groups. Is also going to satisfy this. And one thing I really want to sort of highlight here, where this oligomorphic condition is sort of secretly hidden in these rules, is if you want any category of G sets to be a pre-Galois category, you're sort of forced into the oligomorphic setting pretty quickly. And so the issue is, when you start taking products of G sets, you still need finitely many orbits. And that's more or less the definition of an oligomorphic group, or this local precompact condition we had for admissible groups, is exactly forcing that the product of two smooth G sets has finitely many orbits. So in some sense, if you have any hope of some category of G sets being pre-Galois, you're forced to be oligomorphic right away. And well, the theorem, and this is a theorem of Andrew and I's, is that this is everything. So every pre-Galois category kind of looks like this.
So looks like this means it's representations of a G admissible group.
it's the category of smooth G sets for an admissible group. Yes. Not necessarily a unique one, but that's.
But you said that the fiber factor is unique.
But it's
there's no fiber.
Yes.
But the non-uniqueness is basically this issue that Andrew alluded to of we could, for even the S infinity case, we could take sort of whatever version of S infinity you like. You know, you could take the one where you allow just all permutations of it versus the unit finite ones, and somehow our theory doesn't distinguish between those. So there's a sort of way of choosing a complete one that might make it more unique, but it's not necessarily clear that you care so much about uniqueness. We have sort of there's whole classes of groups that will have sort of the same smooth G sets, even though the non-smooth things might be very different. But if we only care about the smooth ones, it sort of doesn't matter.
And if you put moderate growth condition, is it true that you will get?
Yeah, so it turns out you can prove a Deligne type theorem if you like. So I mean, I think what you want is if you have a category of G sets, you can sort of define like Schur-Functor type things. So you can send a set X to the set of n tuples of X of distinct elements. That's going to be your sort of exterior power. And if you have the property that every set is killed by one of those functors, then I think you again get a fiber functor too.
And what about the moderate growth version?
I mean, I think that's, well, moderate growth. Yeah, I mean, I'd want to think more about. Yeah, I think if you just have moderate growth, yes, I think that's. Yes, I think that should work.
That's fine because you have an oligomorphic. We know it's an oligomorphic group, right? If you have an oligomorphic group with moderate growth, it's obviously fine.
Yes. Yeah, that's right. So yeah, it is. You have the analog, and we'll see in a second. You can actually deduce one from the other.
What's the distinction? So Andrew explained that admissible oligomorphic group is smaller.
Yeah, you should think like finite groups are automatically oligomorphic, but pro-finite groups are just admissible. So that's the analogy.
Oligomorphic. So admissible groups is like a pro-oligomorphic.
That's what you should think. Yeah, it's maybe slightly false, but that's yes. Admissible being pro-oligomorphic is the right way to think about it. And if you have something that's sort of generated by finitely many transitive sets under these operations, then it will have to be oligomorphic and not admissible, or not like genuinely admissible. So,
and what about the question about growth? Can you have arbitrary growth?
Yes, we can have arbitrary growth. So for oligomorphic groups, there are examples where, yeah, the number of these things grows arbitrarily fast. So like, any function you can define from the natural numbers to the natural numbers, there's an oligomorphic group that grows faster than that. So it's
Schur-Functor, vanishing of Schur-Functor equivalent to moderate growth.
Yeah, that's sort of what I was saying. Either of those will be equivalent to having a fiber functor, which means you're actually like a finite group or a pro-finite group. So it's all, yeah, the finiteness stuff is very analogous. I guess
so you can always linearize and you will get a symmetric monoidal category, but in order for it to be rigid, you need a measure, right?
Let's just hold on. There's some work to be done there. Yes, let me just say briefly. I guess I don't want to go through this too much, but I'll sort of elaborate on how this works. So if we're back in the finite, so say that G is finite for now. If G is finite, this fiber functor to finite sets, okay, it's it's the forgetful functor to sets. We can sort of also realize it, or well, one choice of it, I guess, is to take Harm from G to your, right? So if I think of G as a G set for itself, then the fiber functor, I can sort of realize it as a Harm set internal to my category. And then this fact that when we realize that G is also the automorphisms of this functor, it sort of comes down to the fact that you now have two actions of G on this copy of G, on the sort of Tensor version of G, left multiplication and right multiplication. And those commute, and they're sort of, I want to say like sort of a double centralizer type property. So if I look at permutations of G that commute with left multiplication, that's exactly right multiplication. So this fact that the automorphisms of the fiber functor are just G itself really comes from this kind of basic fact from group theory that left and right multiplication are kind of double centralizer. And so the idea of the proof is we construct G as a kind of G set, but really in this ind category of our pre-Galois category C. So we construct something that kind of plays this role of a torsor, and then the group itself will act on it kind of on the other side. This may be a little bit oversimplification, but that's the idea. So
even if your group is profinite, it's still int.
Yeah, even if it's profinite, we're okay.
Construct a ring of smooth functions, basically.
So far, no. Everything is just, there's no, this paper where we're talking about pre-Galois categories, there's no tensor categories. There's no.
No, but I mean, it's analogous to.
Oh, yeah, it's very analogous. It's very, yeah, this object, if you linearize it, you get more or less this algebra this smooth group algebra type thing.
Functions on the fundamental group of the case.
Maybe it's actually pro-C, which explains the profinite group.
Yeah,
Oh, pro-C, yeah, maybe,
yeah,
it's an inverse. You're right, it's an inverse limit of them. There we go. That's a good point. But okay, so this is a nice thing. So in some sense, this we can think of this as we took a discrete version of pre-Tanakhian categories and we answered this classification theorem, like more or less completely. But I do want to return to the world of symmetric tensor categories, the stuff that we're all here to hear about. But I guess before I do so, is everyone okay with this? So I would say constructing this thing is really getting into kind of where these oligomorphic groups show up. So these show up in model theory. There's this whole language of Frazee limits, and oligomorphic groups are naturally automorphism groups of Frazee limits. That's kind of why model theorists defined them and studied them. And we sort of run a version of Frazee theory inside our category to construct this. So that's maybe a little bit of the motivation. Was there a question?
Yeah, Victor had a question.
Yeah, I just want to ask where this non-uniqueness of G shows up in this proof. So, I mean, you construct this object, which is canonical, probably.
Yeah, so I guess it's this problem that we sort of can't distinguish between all of it because we have this like smoothness condition.
So the group can have kind of dense subgroups. Yes? You can replace a group by dense subgroup.
Yeah, you can replace a group by a dense subgroup, but it doesn't.
No, I understand, but in this proof, I mean, you should make some choice.
Yeah, so we do have a sort of preferred choice, and it will be a sort of, there's a completeness condition you can impose. And so that would be like the full infinite symmetric group would be the complete one, and that's the one it'll pick out. I'm sort of suppressing some stuff here. There's also some countability things that you might want to worry about and deal with, but in sort of reasonable cases, this is kind of how it works. All right, let's go to pre-Tanakian categories.
But if you impose completeness, will you get some sort of uniqueness statement?
Yeah. So there is a unique complete one. Maybe again we want to assume like a countability hypothesis in that case.
And the functor to all like capital sets, what will the automorphism group of that be? Will that be?
That's messier because you don't want to. You have to then worry about the topology. So it's like the functor to all sets is not the right thing to consider. So it's a little. Let's see. All right. I want to make sure I didn't miss anything. All right. So now let me get to the next part of the talk and talk about pre-Tanakian categories. But okay, so suppose I have an object A inside some category C, and this is going to be a pre-Tanakian category. And I want this to be a associative commutative unidal algebra. All right, so I'm going to start looking at algebras inside pre-Tanakian categories, and I promise it's going to connect back to things in a second. And so what I can do is if I have such an algebra, I can take A, I can I have the, I guess, co-evaluation map to add in a factor of A tensor A dual. Then I can multiply these two factors to get a map of A tensor A dual. And then I can evaluate to 1. So automatically, if you're an algebra object in a pre-Tanakian category, you come equipped with a trace form. Right? And then in particular, I can use this to define a trace pairing. So let me take this whole thing to be epsilon. I can do a trace pairing where I take my algebra, tensor itself, I multiply 2 elements, and then I take a trace. All right, so I have a trace form and a trace pairing. On any algebra in a pre-Tanakian category, and of course, like even if I'm not in a pre-Tanakian category, I really just need A to be a rigid object that is also an algebra to make this work. But I'm going to assume everything's rigid, so we always have this, and then I'm going to say that an algebra is a tall. A is a tall if this pairing is non-degenerate, if it's a perfect pairing. Okay, so this is some class of algebras in any pre-Tanakian category that you can define. And as a sort of sanity check, so let's say I'm in So C equals rep G, and maybe K is algebraically closed. Then, well, okay, what are the étale algebras? Well, if I just take an étale algebra in representations of G, and I look at it as just an algebra with a G action, that algebra is also an étale algebra over an algebraically closed field, which actually means that as an algebra, it's just isomorphic to k to the n for some n. If we weren't algebraically closed, we might have to deal with field extensions. So I'm just k to the n for some n as an algebra, but I have an action of G on this. And so G is acting, but it's acting via algebra homomorphisms now. So if G is acting on k to the n via algebra homomorphisms, it acts on the maximal ideals. So G is acting on spec of k to the n, but this is just n points equals, n points. Okay, so étale algebras in rep G in algebraically closed field, they're really just, you take an action of G on a finite set and you linearize it. You look at maybe functions on that set, and that's an étale algebra. Okay, so this turns out to be the same as special commutative Frobenius algebras. They're sort of automatically, under these conditions, you also have a co-multiplication and stuff, but we're not gonna, we'll stick to this étale algebra setup. All right, so we have this nice class of algebras, and as I just sort of pointed out, in the case where we have representations of a group, these are exactly picking out for us the stuff that is coming from a G set. So you might be thinking, what can I do? How is this possibly going to connect to the first half of the talk? Well, what we can do is I can define maybe 8 of C to be just the category of étale algebras in my pre-Tanakian category with algebra maps between them. Okay, so not every G linear map between étale algebras is an algebra map, but some of them are. And in fact, what we actually want is then the opposite of this. So if I take, I just won't even introduce new notation for it. I'll just call it 8C op. So I'm taking, algebras in C, algebra maps. I'm taking the opposite category. If you like Frobenius algebras, I said every étale algebra has a co-multiplication. This is just co-algebra maps between these étale algebra objects, if you prefer that. And maybe the theorem is that this category of étale algebra objects, opposite, is Pre-Galois. For any pre-Tanakian category. So, I was, but that's the main, the main takeaway here is that the étale algebras, the Frobenius algebras in a pre-Tanakian category, always come from an oligomorphic group. And we think of the associated oligomorphic group as being something like the component group of your group. So maybe I'll let you guys ask questions.